So the acceleration of the box relative to the truck bed is acceleration of the box minus the acceleration of the truck bed. Just as we would subtract the 8 meters per second going from the frame of reference of the road to the frame of reference of the truck bed, we would subtract the accelerations, and we would get 2 meters per second squared. So if you're sitting in the truck bed, the brakes are engaged, and the box appears to accelerate forward at 2 meters per second squared. And relative to the truck bed, that is its acceleration. So relative to the truck bed, that is, well, that acceleration multiplied by the mass of the box is the net force. If you were trying to hold that box back, if there was a spring attached to the gate of the truck and the mass, that spring would elongate to produce enough force to produce this force to oppose this net force. So this isn't just apparent within the frame of the truck bed, this is a real force. Okay, then the displacement in the truck bed is 2.1 meters. Now previously I was trying to use that 2.1 meters relative to the road, and that wasn't very bright. And I got a ridiculous result, which alerted me to the fact, and I'm in kind of a precarious balance here, of my own design. Okay, so the delta S is this. So the change in kinetic energy is equal to the work done by the net force, again, relative to the truck bed. And we multiply that out. Mass of the box times 2 meters per second being the force, 2.1 meters being the displacement. We get 4.2 meters squared per second squared times the mass. That's going to be the change in kinetic energy. Now the initial kinetic energy, and I've got F net, and that's an REL relative, and this is a delta S relative to the truck bed. So the initial kinetic energy relative to the truck bed is 0. It's not moving relative to the truck bed. The box is not moving relative to the truck bed. So that the final kinetic energy, and I've started dropping the relative subscript here, but the final kinetic energy is then going to be, what, 1/2 mass times the final velocity squared. Again, all relative to the truck bed. And that's got to be approximately equal, well, it's got to be equal to the change in kinetic energy. The final kinetic energy is equal to 1/2 mass times final velocity squared, and it's equal, since the initial kinetic energy is 0, to the final kinetic energy, to the change in kinetic energy. Well, here's the change in kinetic energy, that's equal to the final, so 1/2 mvf squared is equal to this, and we conclude that Vf is about 2.8 meters per second. Might be 2.9. When I calculate things over here, I get something closer to 2.9, but I used approximations here as well. Had a little bit of an overestimate in the time. Now let's see how that relates to what we would have gotten here, because I didn't finish this. I kind of left it for you to finish. Remember that the 1/2 meter per second squared times t squared was equal to the 2.1 meters, because that 1/2 meter per second squared times t squared turned out to be equal to the difference in the initial positions of the box and the end of the truck bed. So solving that for t, we get t somewhere between 1.4 and 1.5 seconds. Closer to 1.5, so I rounded to 1.5. I won't even swear to the fact that it's between 1.4 and 1.5, but I'm pretty sure it is. That's the time from the, that's the time on the clock, if the clock started when you first hit the brakes. So the time interval during which the box moves is 1.5 seconds. Its acceleration is 2.45 meters per second squared, and we simply multiply that by the 1.5 seconds to get negative 3.7 meter per second change in velocity of the box. So relative to the road, the box slows by 3.7 meters per second. The change in velocity of the truck bed relative to the road, calculated the same way with the same time interval, but of course with the acceleration of the truck bed, is negative 6.6 meters per second. So what's going to be the relative velocity of the box with the truck? The end of the truck bed slows by 6.6 meters per second. The box only slows by 3.7 meters per second, meaning when they collide, the relative velocity is going to be this minus this, which is 2.9 meters per second, comparing quite well with the 2.8 meters per second. And if both calculations are done all the way through with equal, without making, well, let's say you're going to have to make approximations to get the numbers, but making minimal approximations, they will agree to many decimal places, okay, depending on where you make your approximations. So both analyses are valid. This one is a lot shorter than this one or this one. And of course you could figure out, you could solve this one for the time also, and you would still get relative velocities. Relative velocity would still be the same as it is here. And you should probably check that out.